Welcome to the 37th ACM Symposium on Applied Computing, SAC 2020. Today my presentation title is Sparse Tensor Storage by Tensor Unfolding. Here I am Shafat Hossain and there are also a member named KM Azharul Hassan. All of us are from Department of Computer Science and Engineering, Khulna University of Engineering and Technology, Kuwait, Khulna, Bangladesh. Let's see the next slide. Abstraction. So before going to start my presentation, I want to talk something about what we actually did in our paper. We described a new sparse storage format that provides storage benefit and are independent of to number of dimensions of tensor. That means our algorithm is not dependent on any number of dimension of a tensor. So it is independent. For this implement this algorithm, we designed an efficient hash function to store sparse tensor data. The hash function converts a higher order tensor to a matrix by tensor unfolding. And using the unfolded matrix, we developed algorithms to store non-zero data based on the sparse fiber. So we call our scheme unfolded compressed row or column dependent on the row basis or column basis fiber. And short form of our algorithm is UCRF or UCCF. Our approach experimental results shows that superior performance with standard dataset comparing to the other important approaches. So let's see the next. Introduction. So here first question is arrived at what is tensor? Tensor are data structure that represent multi-way data. That means more than two-dimensional matrix is called tensor. So here you can see that this figure is represent the tensor and this is the represent this matrix and these two represent row vector. This is row vector and this is column vector and this is scalar. So recently tensor have become more popular in communities such as data mining, recommender systems and health informatics and many other things. Tensor used in data analysis in multi-dimensional array MDA. The number of dimensions that tensor has its order. That means the dimension represents the tensor's order. What order tensor is it? It represents on dimensions. So scalars are zeroth order tensor, vectors are first order tensor, and matrix are second order tensor. And tensor can be sparse or dense. Sparse tensor contains the most of the values are zero and dense tensor contains most of the values are non-zero. Facebook activities, Amazon reviews are conveniently cast as sparse tensor. The Amazon reviews tensor in particular contains 1.5 into 10 to the power 19 components corresponding to 10 to the power 7 hexabyte of data, assuming 8 bytes are used per component, but only 1.7 into 10 to the power 9 of the component are non-zero. So here you can see that we lost a lot of memory to store the zero element with non-zero element. If we can remove this zero element and only store the non-zero element of a tensor, then we can save our memory storage. Real-world tensors are enormous in size and are often very sparse. Hence, it is a charming need for efficient and high-performance tools capable of processing the massive sparse tensor for high-performance computing. So here, compressed sparse row or column storage, which is nowadays most popular format throughout the high-performance computing. CRS is the so popular mainly due to its simplicity, but CCS has higher space requirement when number of dimension is large. There are so many other space tensor storage format like coordinate format, compressed space fiber, block compressed space row, W compressed space row, but all of them are not suitable for all kinds of dimension of tensor. So for this purpose, we introduce our approach to reduce the zero element and only save the non-zero element of a tensor. So next, so Here we can see that there are a lot of tensor stress format and all are not suitable for every application. The uses of the format depend on the structure, sparsity, computation and hardware architecture. So among them, coordinate format is the most popular approach, but it is rarely used due to its space efficiency. Compressed sparse row is another most popular storage format, but it is not efficient when the dimension is increased. Compressed sparse fiber is another approach for and it compresses every dimension of a tensor. So tensor. But CSF needs many auxiliary table when the number of dimension is high. That means it needs more storage than any other to store when the dimension of a tensor is increased. So there are also a tensor stress format, compressed sparse block, CSB. It is also not suitable and it is the represent a matrix of a dense collection of sparse block stored in coordinate format. The block compressed sparse row format generalized CSR. That means it represent and it some modification of CSR algorithm, but it is not the suitable for a higher order tensor. And there are also a approach that is W compressed sparse row format, and it is also extended format of CSR, but it is not suitable. So among them, there are a lot of algorithm, but all are not suitable. To implement our UCRF, we have to know about tensor unfolding. So what does it mean? Tensor unfolding is the process of reordering the element of n array into a matrix. For n order tensor, it is often useful to be able to represent a n order tensor as a matrix. It is often called matricization or flattening of tensor. So to fully capture this silent information, we have to need three pieces of information. As one of them are tensor data, second tensor size, and third one is the converted dimensions that are mapped to the rows of the matrix and the converted dimension that are the map to the column of the matrix. So this figure represent the five-dimensional matrix and it is the unfolded tensor matrix of five-dimensional tensor. Suppose we have to unfold it n order tensor T into T prime, where L1 prime and L2 prime are the length of the dimension D1 prime and D2 prime, where D1 is column row dimension and D2 is column dimension. And for calculating L1 prime, we have to multiply all the odd dimensions length, and for L2 prime we have to multiply all the even dimension length. To calculate R and C, we have to follow this formula. The mapping function that converts x1 x2 dot dot xn to x1 prime and x2 prime by this formula. This is three-dimensional tensor whose length is 2 into 4 into 3, and this is the unfolded matrix of this tensor. So let's see the next slide. This is the coordinate format of 4-order tensor, and this is the unfolded coordinate format of that tensor, and this is represent the two-dimensional matrix coordinate format. So fiber of tensor. Fiber is extracted from an n-order tensor by fixing every index except on, and it is called an on-dimensional fragment of tensor. For the third-order tensor, three types of fiber can be obtained, that are column fiber, row fiber, and tip fiber. Column fiber, row fiber, and tip fiber are notified by this way. Here figure A is the unfolded row fiber of four-dimensional tensor, and this figure B represents the unfolded column fiber of four-dimensional tensor. So this is the graphical representation of conceptual row fiber tree for unfolded tensor, and this is the conceptual column fiber for unfolded tensor. So here you can see that we need 4 vectors to represent our algorithm to store the non-zero element. RF hold the row index that has minimum on non-zero element, and FPR represent how many non-zero element has on that particular row. CC holds the column index which has non-zero element, and VL holds the value of the non-zero element of the particular position. Figure B, storage scheme for column fiber is the same as storage scheme for row fiber. Here CF represent the column index of non-zero element that he holds, and FPC holds the number of non-zero element of that particular column, and RC the holds the index of row which has non-zero element, and VS the represent the non-zero element of that particular position. So this is the tensor storage by logical unfolding. Here we do not store the unfolded tensor and the unfolded fiber. Therefore, without creating the T prime, we create the UCRF and UCCF from the original tensor. Hence, the idea of unfolding the tensor is logically in our scheme. The x1 prime and x2 prime is calculated directly from T according to the computation technique of without converting the T prime. So it is save our time. To implement our algorithm, we take Core i3 processor and 4 GB RAM. The algorithm are implemented in C++ and compiled with GCC compiler. The proposed UCRF scheme is compared with compressed row storage scheme and compressed sparse fiber. This is the description of our dataset. We use two types of dataset, real dataset and synthetic dataset. For real dataset, we collected data from FOST, and we collected 4 types of data from FOST website. And the sparsity rate average is 99.00, and the sparsity rate for synthetic dataset is all average 98.00. So this is the graphical representation of our experimental results. Here blue color represent the UCRF and orange is CRS, and gray color represent the CSF. And we can see that our implemented algorithm shows the best performance among this algorithm for both real dataset and synthetic dataset. So this is the storage cost per non-zero element. Here you can see that our UCRF, here you can see that our implemented UCRF need lowest bytes for store the per non-zero element for both synthetic dataset and real dataset. Conclusion: the proposed unfolded compressed row and column fiber allow to store any dimension tensor data in less memory bandwidth. Compared our UCRF UCCF scheme to CSR and CSF schemes. Among them, our tensor scheme performs well. One important future direction of the work is to implement the higher order tensor operation using UCRF and UCCF scheme. So that's all my presentation, and there is some important reference that we follow. So thank you all for giving me a chance to represent my paper in this presentation. Thank you all.